Hello and welcome back to my Applied Data Science channel. My name is Ioana, I'm a senior data scientist, and in this video we are going to step in the world of natural language processing. If you want to stay interview sharp in 2024 and nail that data science job that you've been dreaming of, you must learn about large language models. There is absolutely no reason not to add this project to your portfolio. Even if you have a CPU-only computer, like I have, even if you are on a budget, this is a completely free solution. So you can 100% follow along and familiarize yourself with how to build a chatbot. We put together LangChain, Ollama, and Hugging Face and build a RAG system that can run locally on our computer. The goal of large language models is to communicate with humans. For that, the LLMs must learn to generate text as similar as possible to human language. For that, the LLMs must first learn from examples, thousands of gigabytes worth of text. In a simple user-chatbot interaction, the user makes an inquiry and the chatbot answers it in a human fashion. The chatbot listens from two directions. One is the user, and the second are the rules that must guide the general behavior of the chatbot, and these are set by the developer. As the purpose of the large language model was to learn the semantics and the rules of the language, its answers are going to be quite general. Think of it as a generalist that knows a little bit of everything but has no in-depth knowledge of a particular domain. A chatbot can specialize in a particular topic by having access to organized domain-specific information. This is called RAG and it stands for Retrieval Augmented Generation. It involves providing domain-specific information in an organized manner and also having the LLM agent listening from three directions. First, the user input, secondly, only the relevant information, which is also called context, and thirdly, the general rules that must guide the behavior of the large language model. Let's focus on what I mean through organized domain-specific information. More like in a library where books are organized based on their characteristics, like the author or the genre, the information that is similar will be grouped together and far away from the dissimilar information. The information comes in text format, like documents, like PDFs, some website, or whatever text information. First, these documents are going to be split in smaller chunks of text, such that they are easily manageable. Then, the features of these chunks of text are going to be extracted. We are going to use an embedding model in order to extract these features, such that at the end, the features are going to be a numerical representation of the text chunk. These embeddings or these vectors of numerical features are going to be stored in something called vector store, which is nothing else than a space where all the similar items are grouped together and far away from the dissimilar ones. So you can think of it as a clustering, but in a very high dimension. If you are familiar with concepts such as corpus, embeddings, or tokenization, you can skip the next section entirely, but if this sounds new to you, I think this explanation is going to pay off. To understand the intuition behind embeddings in general, imagine you are playing a game with your friend. She has to guess the object by looking at the shadow projected on the wall with a flashlight. The first obvious thing is that your friend has limited information to guess from. The Rubik cube over here is three-dimensional, but the projection on the wall is two-dimensional. There is additional information which is missing, like for example the colors or the fact that the parts of the cube move. You could help her by moving the flashlight in different positions. This would result in different 2D projections on the wall. The shadow on the wall is the embedding. It is a low-dimensional representation of something, and that something could be an image, an object, a piece of text, or whatnot. The flashlight is the embedding strategy. As you might have noticed already, it is very important because different angles give different outputs. Ideally, the embedding model would give the richest lower dimensional representation of the input. Going back to our project, a text embedding is the result of applying some function to text input data. The embedding itself is a numerical representation of the text. That is a vector of numbers, like here in the image. And this vector has different lengths according to the embedding model. It can be 512 dimensions or 1024 or even 2048 dimensional. You might ask yourself now, how does a sentence have more than 2048 dimensions? So before going in the embeddings stage, the text undergoes some processing. The text in all of our documents is called a corpus, and each phrase within the corpus is split into tokens. That's called the tokenization phase. And for simplicity, let's think that each word in the phrase is going to be a token. Then, with all of these tokens, a vocabulary is created. That is a collection of all the tokens in our dataset. In order to go from text to numbers, a one-hot encoding can be performed. Each position in this high-dimensional vector is representing one of the words in our vocabulary. And for each one of the phrases that we have over here, on the position of the word in the phrase, we are going to put a 1, and then if the word doesn't exist in the phrase, we are going to put a 0. So in the end, we are going to have a one-hot encoded vector with ones on the positions of the words that exist in the phrase and zeros on the other positions. And these are the high-dimensional input vectors that actually will go into the embedding model in order to generate a lower dimensional output of 512, 1024 or 2048 numbers. So now let's see how we can implement this in code. The first thing that I did was to create a virtual environment, and inside this virtual environment we must install, using pip install, all the libraries that we need. And for this particular case, we need to install LangChain and LangChain Community. And then from LangChain Community, we need to import PDF directory loader, because this is what we are going to use in order to load our documents from a folder. Our documents are going to be some user manuals for the EcoFlow batteries and power stations. And what we are going to aim with our RAG system is to be able to answer technical questions to the users that have problems with their products. So we are going to load all these PDF user manuals from a folder that we've created over here, and this folder is called user manuals. So first of all, we are going to use PyPDF directory loader and load our manuals. If we want to see how our documents look like, we can simply access them. So we see that we have a list over here, a list of document objects, and this document object contains some metadata, which indicates which is the PDF from where the information was extracted, and then the number of page. So this function, what it does, it loads each page from the PDF file as a separate document. And now if we inspect a little bit this text, we see that we have some weird characters. So what I had to do next was to process all these strings under page content, and these are all the changes that I've done. So now if we access our documents once again, we are going to see that they look cleaner now. It is very important to clean the data because it's on the principle garbage in, garbage out. So you would not like your chatbot to answer with some weird characters when a user asks a question. I was telling you before that each one of the documents has to be split in smaller chunks that are more manageable. And for that we are going to use the recursive character text splitter, also from LangChain. The parameters over here, chunk size, means that we are going to keep in one chunk only 700 characters, like 700 letters, and punctuation marks, spaces, and then we set here the chunk overlap to be 50. The last 50 characters of the first chunk are going to be repeated as the first 50 characters from the second chunk, and then the last 50 from the second chunk are going to be the starting characters of the third chunk, and so on. So we are going to do this because we need to preserve some context from one chunk to the other. Now that we've set our rules for splitting the documents, we are actually going to split the documents by calling the method split documents on our document list. We can see here that initially there were 8 documents, so 8 pages of user manual in total, and these were split into 25 documents. Actually, these are 25 chunks of text. And now the next thing that we'll have to do is to generate text embeddings of these chunks. There are multiple ways in which we can generate embeddings from text, but from my experience, there is a particular group of embedding models that perform quite well, especially on the English language, and they are free, they are open source and available on Hugging Face. And you can simply import them from LangChain community embeddings, Hugging Face BGE embeddings. They have a small embedding model, a large embedding model. You can go on Hugging Face Hub and then check there all the options. I'm going to choose the BGE small, and this is going to be my embedding models. I'm also specifying here the device to be on CPU, and I'm going to normalize the embeddings. So now if I want to see how these embeddings look like, what I can do is say Hugging Face embeddings and then call the embed query method and just pass in some text that I want the embedding model to extract features of. And then I can see over here, if I call this object that was created, this is the actually embedding of the text, hello my dear friend. And as we can see, there is a list of numbers. And now we can check how long this list is by using the length method. We took this string, this text, and we extracted features of this text, which are now a numerical representation of size 384. Now that we've set up our embedding model, the next thing that we'll have to do is to decide which is the vector store that we are going to use in order to organize and in order to store all these vector embeddings, these characteristics. And from LangChain community vector stores, we can import different vector stores. Here I've chosen Fice, but you can also go with Chroma or whatever vector store there are available over there. And then what you can do in order to create the database is just call the method from documents and pass in the list of document chunks that we've generated previously, as well as the embedding model that we want to use in order to extract the embeddings of these chunks. We are going to store these embeddings in an object called DB, which has really nice properties, such as the possibility to save it on our local disk. And this way, we won't have to create the vector store every time we run the code, but we can just load and have complete access to our vector store. This is going to generate a folder that I'm going to show you right now. This is test files index, and this is going to have two objects, the index.files and the index.pickle. So if you'll have these two files, it should give you the certainty that your files index was correctly created, and then you can just load it and pass it to a new object by using files load local, and then pass in the folder path to this folder that I've shown you. Also, you must specify which embedding model you are using. So here you are going to specify Hugging Face embeddings as we've previously created it. And now let's just load our files index from local. Let's query our vector store. I've already created a query here. It rained on the battery and now it is not working. And what I have to do now is perform a similarity search of my query that I've written over here against all the feature vectors in the vector store. And this is going to retrieve the relevant documents, the relevant information that are similar to the meaning of my query. So now let's check exactly what do I have in these documents. So I can see here, for example, that I have a word waterproof, do not immerse in water. Then here I have moisture. Chunks of text that are similar to my query are all related to water and damage because of water. And this is actually what I mean by relevant context. These are going to be the context that I'm going to pass to my LLM agent together with the query, which is the user input, and together with the prompt, which are the set of rules and instructions based on which the LLM agent must act. Here I've showed you how to retrieve similar chunks of texts from the vector store, but now we are going to set up the retriever. And for this, on our vector store, we are going to call as retriever and then just tell it which should be the search type, and we are going for similarity because we want our retriever to return those chunks of text that are similar to the query, and also we want the most similar three pieces of information. By the way, if you've come this far and you like this tutorial and would like to learn more applied data science from similar tutorials, hit the subscribe button and like the video so I know you are here. So now we are ready to set up the large language model, which is going to handle the user input and also generate the answer to the user. And the first thing that we need to do for that is to go on the Ollama website and download Ollama on our computer. You can press download and this is going to open a new window where you can choose exactly your operating system. So I've chosen my operating system to be Windows, and then just download for Windows Preview, and this is going to download an executable file that you will later need to run in order to install Ollama on your computer. And it might be actually that you will also have to restart your computer before being able to use Ollama. But once you will go to your command prompt and write in here Ollama, this should show you something like this, where all the methods of Ollama are available. So we have serve, create, pull, when we want to pull a model from a registry, and let's see exactly what this means. On the Ollama website over here you have models, and then under models you will see there are multiple large language models available for use. You can choose Mistral, which is very good. You can use Phi 3, which is very small, or like whatever, Lava, if you want to also use images and text. So this is going to be a multimodal model and whatnot. You have all these options over here. But when you install Ollama, it doesn't come with all these models inside it. You just have to pull the models in order to use it, the same way you pull code from GitHub, for example. To pull a model from the registry, we need to use Ollama, pull, and then the name of the model. So we can do Ollama pull Phi 3 mini, for example. This is how you actually access a model, but you can find more information about this on the Ollama website. Let's just jump into the second stage of the RAG, which is putting together all the pieces of the puzzle. The first thing that we are going to do is import all the necessary packages. From LangChain community LLMs, we are importing Ollama. Import the chat prompt template in order to define the prompts. And then the LangChain chains for retrieving this prompt template is the stage where the developer is telling the large language model how to behave, which are the rules that the large language model must abide. Maybe, I don't know, like you are a friendly call center agent, or your task is to translate text from one language to another, or whatever the use case of this LLM is going to be. So because we are working with a call center agent, I want the LLM to be friendly and help the customers with the technical issues. And there are two important pieces of information that I have to include in the prompt template when building a RAG system, and that is a question can vary from user to user, or even the same user can ask multiple questions, and also a context. And then here in this context, I need to input the useful information, the relevant information based on the question of the user. So the context is also going to vary with the question of the user. So I'm going to use chat prompt template from template, and here I'm passing in exactly this string that I've defined here with the rules and my variables. And then from Ollama, I have to install the large language model that I want for text generation. And for this case, I'm going to actually use Phi 3 mini. Mistral is really good, but it takes much more time to generate the answer. But you can also play with it or with other models. And then what I need to do is define my question answering chain. So first of all, here I'll have to input the large language model that I need for text generation. Then I'll pass in the retriever. This retriever is responsible to provide the relevant context to the user question. And here, as you can remember, we are only going to keep or extract, we are only going to retrieve the 3 most relevant text chunks from our vector store. And then we also want to return the source documents, and this is something very useful when you want to check if your chatbot is hallucinating on the information it returns, or if there is actually some base to the information it gives the user. And then here in chain type KV args, we are going to pass in the prompt, which we've here defined earlier. Now we can invoke this retrieval QA by using the method invoke and passing in the query of the user. So my battery doesn't charge, ? is going to retrieve the 3 most relevant pieces of context, pieces of information from my vector store for this particular question. So it's going to do a similarity search between this user query and the vector store. I have my large language model, which based on the prompt that contains both the user query and the context and the rules by which the LLM has to behave, is going to return an answer to the user. It is not a production-ready workflow that you can use, because nobody is going to wait for like 2 minutes in order to get an answer. But it is something that you can use in order to learn how to build LangChain pipelines, how to build like chatbots or RAG systems and whatnot. 3 minutes later, we also have our answer. For the query, my battery doesn't charge. The chatbot is going to answer, "Hello, this is Diego from EcoFlow support. I understand your concern about charging. Firstly, ensure you place the River Pro Extra battery on a non-flammable surface." Okay, and then further information in user manual at pages 2 and 5. That was it for this video. I hope that you've learned something useful. I hope that you are going to use all this information in order to practice how to build a RAG system, how to put together this puzzle of LangChain and Hugging Face and Llama, and how to actually leverage all the information that there is out there for free in order to power up your skills. If you want to see more similar content and learn applied data science from this type of hands-on tutorials, do not hesitate to like this video and hit the subscribe button. I hope to see you next time. Bye bye!